educator Carlos Plain of Durham School states, "I went through my whole time on Earth engaging and communicating a speculation of the universe. Moreover, finally the theory is being tried. I invite that since that is the manner in which we push ahead, that is the way we make progress in science. The James Webb Space Telescope is disturbing an outstanding proportion of what has been viewed as truth in cosmology. For the new year, another ultra-deep image shows that we have serious goofs in cosmology. The telescope, which ought to show us the crucial stars of the universe, is developing into an enemy of the past point of view. Furthermore, it might present to us a completely dumbfounding science. Not all specialists are cowering in fear at the new realities. Other accomplished experts welcome the progression, since it has long been clear that something was the matter with our old theories. The deviation in the appraisal of the progress speed of the universe alone ought to have shaken experts' perceptions long ago. Yet, bringing all that into account, they adhered to old hypotheses. The cosmic microwave background radiation, CMB, considered the oldest light known to man, was created approximately 380,000 years after the Big Bang, right when the universe had cooled enough for electrons and protons to form stable hydrogen particles. Scientists call this process reionization, which made the universe transparent to light. The CMB was first seen in 1964 by American physicists Arno Penzias and Robert Wilson while they were working on a new type of radio-receiving antenna technology. This discovery was, for a long time, seen as one of the strongest pieces of evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize. At a specific point in the history of space science, the CMB most reasonably provided a perspective on the early universe, with small temperature differences giving fundamental information about the conditions shortly after the Big Bang. Theoretical researchers incorporated the CMB as a cornerstone of the key appraisals of the material universe to measure the progress speed of the universe, among other things. Cosmologist Edwin Hubble had already established this in the late 1920s, discovering that distant galaxies retreat from us and that their speed is proportional to their distance. Today, these observations are known as the Hubble law or the Hubble constant. Hubble, however, did not have the advanced measuring systems available many years later, when the CMB was discovered, which prompted a recalculation of the expansion rate. These recalculated rates were generally lower than Hubble's original estimate. Later, researchers recalculated the rate using Type I supernovae as standard candles, providing stable light that could be used as reliable measuring points. The estimates from the CMB yielded an expansion speed of around 67 km per second per megaparsec, while estimates using supernovae yielded around 74 km per second per megaparsec. What does this error in concluding the universe's expansion speed tell us? Did you know this discrepancy has been known since the 1990s? Since then, experts have known, or at least suspected, that something might be wrong with the assessment of the CMB, the measurement methodologies, or the concept of the universe's expansion. The discrepancy between the observed and expected values of the expansion rate is referred to in science as the SA tension or Hubble tension. The implications of this tension are enormous, indicating that fundamental aspects of how we understand the universe might be flawed. For a long time, experts were puzzled. Since the James Webb Space Telescope went into operation, it has provided scientists with astonishing data that may now shed light on the issue of the universe's expansion speed. With systems so old and mature that their development should have begun theoretically before the Big Bang, this data is overturning old cosmology. Researchers no longer talk about errors or methodological differences. They discuss the crisis in modern cosmology. Not only could the expansion rate be wrong, but the entire concept of expansion, or even the Big Bang itself, is being questioned. Images from the telescope provide evidence of a universe entirely unexpected from what we have long believed. This AA tension was the first warning to experts who still believe in the old theories. Now they face a dilemma. Do we truly understand the universe? Many researchers stand on the remnants of their once brilliant source of both discovery and torment, exploring space with fear and grappling with what they find. Considering the crisis in science, we must ask ourselves, what do we truly know about the universe? To answer this, we need to understand how science works. Theoretical scientists use a complex system of mathematical models, careful data, and analytical reasoning to draw conclusions from the general to the specific. Their understanding comes from a mix of observation, rigorous analysis, and speculative exploration. The term theory itself suggests that these are frameworks and ideas, not definitive facts. The essential raw data we have comes from telescope images, sound waves, and radiation gathered with radio telescopes, as well as the latest data from neutrino observation systems and gravitational wave detectors. With the James Webb Space Telescope, we now have an instrument that can split light into individual frequencies and analyze it in extraordinary ways. Webb can show us the fundamental elements of systems in the early universe billions of years ago. How much mass they contained, how many stars were present, and the shape and trajectory of a galaxy's evolution. However, Webb has its limitations. For example, it cannot always determine whether we are observing galaxies or black holes with massive gravitational forces that shine as brightly as galaxies. We must face the reality that our science has long accepted too many probabilities as facts while dismissing collective explanations. Research has long been confident in its accuracy. The latest discoveries from the James Webb Space Telescope are critical signals to replace theories with new insights. As has happened many times in science, experts are eagerly anticipating new revelations, which are unexpectedly astounding. Many experts are working to develop new explanations. The new discoveries shake the foundations of current science, unsettling many experts. The current models of physical science are still largely based on Isaac Newton's laws from the 17th century. His laws of motion and gravity were the foundation of our understanding of the physical world and the universe for centuries. Newton's principles explain the movement of objects under normal conditions and work particularly well on Earth. However, in space, his theories required refinement, largely achieved by Albert Einstein in the 20th century. Einstein's special theory of relativity, published in 1905, transformed our interpretation of reality, showing that truths are relative to one another and dependent on the observer's motion. His general theory of relativity, published in 1915, expanded on this concept with mathematical descriptions of gravitational properties based on the curvature of spacetime by masses like stars or galaxies. Einstein's principles and ideas were critical in many areas, but he also acknowledged their limitations. He knew his theory would never fully describe the universe and longed for a unified theory, which he never achieved. No other expert has reached this goal either. Wouldn't it be fascinating to know where it lies? Michio Kaku, a prominent astrophysicist from the USA, said in an interview that solving this issue would undoubtedly win a Nobel Prize. Could it? We examine whether the specialists could have missed expected misinterpretations, or whether our telescopes are to be faulted. Dim matter and dim energy are at the highest point of the suspect list for the primary drivers of the cosmological crisis. Our evolving models of the universe suggest that dim matter and dim energy make up around 95% of the universe. However, neither has been directly observed, and their confirmed existence has never been demonstrated. They likely exist in no discernible form, requiring alternative explanations for the universe's expansion and the dynamics of galaxies. On the other hand, they could have properties we do not yet understand. One idea is that the actual properties of dim matter and dim energy have changed over time, possibly exhibiting some form of evolution. Gravity is another theory to be tested. This force, which causes attraction through mass or curvature in spacetime, has not yet been fully explained. The concepts of spacetime curvature, originating from Einstein and widely supported, may need to be revisited. We cannot rule out the possibility that gravity has unexpected properties or that another force is responsible for gravitational attraction between objects. Over time, a few constants have been established in cosmology and astronomy as universal principles. The study of the universe has always been an endeavor defined by our relentless quest for understanding and discovery. From ancient human civilizations observing the stars to modern space telescopes examining the depths of the universe, each step forward in theory and progress has revealed new mysteries while challenging established beliefs. In the field of cosmology, the James Webb Space Telescope, JWST, stands as a beacon of scientific advancement, promising to transform our interpretation of the universe's origins and evolution. Launched with remarkable capabilities, JWST represents a leap forward in observational astronomy, designed to probe deeper into the universe than ever before, with unprecedented precision in analyzing radiation. The cosmic microwave background, CMB, often referred to as the glow of the Big Bang, offers a perspective on the universe as it existed only a short time after its first interaction with light. This ancient form of radiation carries fundamental information about the universe's initial conditions, including its temperature variations, which are crucial for understanding the formation of galaxies and large-scale structures. The difference in the observed values of the Hubble constant, known as the Hubble tension, has been a subject of long-standing debate. It suggests that something is amiss with our fundamental understanding of the universe and its early development. These findings challenge traditional theories and necessitate a reassessment of whether our view of cosmic evolution is inherently flawed. New insights may reveal hidden aspects of the universe's creation, raising questions about dim matter and dim energy, two unexplained components that make up the majority of reality. The progression of science relies on the ability to reshape our hypotheses based on new data. Webb's mission embodies this pursuit, with its discoveries serving as a foundation for future cosmological discussions and offering new perspectives on the universe's mysteries. The future of cosmology may witness significant changes, leading to profound implications for how we interpret the universe, from the Big Bang to the ongoing processes that define its future. The answer to the greatest and most enduring questions may lie beyond our current knowledge, and Webb's observations may prove essential in uncovering new insights that could reshape our understanding of reality itself. The path forward for cosmology and astronomy is filled with potential. Each groundbreaking observation and discovery from telescopes like Webb brings us closer to addressing the most profound questions humanity has ever posed. How did the universe begin? What is its ultimate destiny? Are there other forms of life out there, or are we alone in this vast cosmos? These are questions that may one day find answers, and the James Webb Space Telescope is at the forefront of this grand endeavor. The future of cosmology will likely involve a combination of new technologies, refined theories, and groundbreaking discoveries that continue to push the boundaries of what we know. As we venture further into the unknown, one thing is certain. Science, like the universe itself, is always in a state of constant evolution, driven by the quest for knowledge and the wonder of discovery. The journey to understand the universe is an ongoing mission for knowledge that continually reshapes our perception of reality. As we push the limits of our scientific capabilities, we begin to realize that many of the fundamental theories that once seemed solid are, in fact, open to reevaluation. Advances in astronomy, particularly through powerful telescopes like the James Webb Space Telescope, have opened new avenues of exploration that challenge old assumptions and suggest that the universe is far more complex than we ever imagined. The observations made by JWST, which can look into the distant past of the universe, are yielding astonishing new insights. The telescope is providing unprecedented views of galaxies forming shortly after the Big Bang, helping scientists understand how these early structures developed and evolved over time. By studying the oldest galaxies, we can gain a clearer picture of the conditions that prevailed during the universe's infancy. The ability to explore light from these distant galaxies with such precision offers a direct window into a time when the universe was vastly different from what we observe today. However, the more we observe, the more questions arise, prompting us to revisit established theories and consider the possibility that some of the laws we take for granted may need to be adjusted. For example, one of the most significant implications of recent discoveries is the potential reevaluation of the standard model of cosmology. Data from JWST and other modern instruments suggest that our understanding of cosmic inflation, the rapid expansion of space shortly after the Big Bang, might be incomplete. The results have led scientists to explore the possibility that inflation did not proceed exactly as currently understood, or that alternative models of cosmic expansion may be needed to account for discrepancies observed in the data. In addition to challenging established cosmological models, JWST observations also suggest that the role of dim matter and dim energy, the mysterious components that make up most of the universe's mass-energy content, is more complex than initially thought. While these substances remain undetected through traditional methods, their effects on the large-scale structure of the universe are undeniable. Dim matter, for instance, is thought to be responsible for the gravitational effects that shape galaxies and clusters of galaxies. However, its exact nature remains one of the greatest unsolved mysteries in physics. dim energy, believed to drive the accelerated expansion of the universe, has also become a focal point of cosmological inquiry. The disparity between the predicted and observed rates of expansion, known as the Hubble tension, suggests that unknown factors are at play that we have yet to uncover. This tension between observation and prediction forces scientists to re-evaluate not only the properties of dim matter and dim energy but also their role in the evolution. Scales, perhaps due to factors we have not yet identified or understood. This potential revision of gravitational theory could have far-reaching implications for our understanding of cosmic evolution, galaxy formation, and even the nature of spacetime itself. As technology continues to advance, scientists are not only relying on the James Webb Space Telescope but also preparing for future missions and tools that will further refine our understanding of the universe. Instruments like next-generation radio telescopes, gravitational wave detectors, and neutrino observatories will complement JWST's discoveries, providing a more comprehensive view of the universe from multiple perspectives. Each new piece of data obtained by these instruments will help assemble the intricate puzzle of cosmic evolution. The challenges posed by these new discoveries reflect the very nature of science itself, a constantly evolving field that re-evaluates its foundations in light of new evidence. While the knowledge we gain today may not be the final word on the universe's origins or its ultimate fate, it brings us closer to answering some of humanity's most profound questions. As we continue to explore the unknown, the potential for discovery remains limitless. Each breakthrough brings us one step closer to understanding the vast, complex universe we inhabit. Through these advancements, the future of cosmology is bright, promising new revelations that will reshape the way we think about the universe and our place within it.